Hey, this is Horner, and this is 2004 Mechanics C, AP Physics C, number 2, and we're going to work through this problem. So we've got a solid disk of unknown mass and radius r. It's pulling a pulley in a lab experiment. A small block of mass m is attached to a string. The other end is attached to the pulley and wrapped around several times. The block of mass m is released, and it takes a period or a time t to fall a distance d to the floor. So the first thing they want us to do is calculate the linear acceleration. This one's pretty easy to do. We know the final position is equal to the original velocity times time plus 1/2 at squared. And here we know that x has got to be equal to d. You have to use their terms. And our original velocity is equal to 0. So now we can say d is equal to 1/2 at squared. And then make sure you solve it for a. That would be 2d over t squared. If you don't, you will not get that other point. So there's actually 2 points here, one for this equation with the supporting evidence, and one with this equation. So 2 points on that part so far. Let's go ahead and take a look at the next page. On the next page, it gives you a chart, and usually when you see a chart, you know you're going to have to linearize something. So here we've got distances that it travels and the time it takes, and they want to know what quantities should be graphed in order to best determine the acceleration of the block. Explain. So here we have to explain our reasoning. We know that we need to do d versus t squared. And if we do that, the acceleration will be equal to 2 times the slope. You have to say both of those things in order to get both of the points. For the next part on the grid below, they want us to plot the quantities. So first thing I would do, and they won't give you points for this, but the first thing you need to do is do t squared. And then we've got to put all of our values in. So this would be 0.46. This one would be 1.01. Next one would be 1.42. And finally 1.9. Now we need to plot using those values so that we get our straight line. And you want to do 0.5 here, 1, 1.5, and 2. Here we're going to have 0.5, we're going to have 1, 1.5, and 2. So now we've got all those things set up. Your points should be something similar to kind of what you see here. These aren't going to be perfect, but they're close. And then you're going to have a best fit line that does start at 0, and it will just move right up kind of through those points. So there's several points here. One of the points you get is for using the correct data, for plotting it correctly, which means that you have to have your axes. Actually, make sure you do this, and we need to do this. T squared is second squared. Next thing we need to do is make sure that we have the curve correct, which is actually a best fit line. Next thing they want us to do is use our graph to calculate the magnitude of the acceleration. So I know acceleration is 2 times the slope. So that would be equal to 2, and then we've got to use points from the line. So we'd actually just use points from the line. Don't try to use the points they give you because they won't give you credit. So this would be 2 minus 0.5, and then that's divided by something like 1.97 minus 0.5. And you should end up with 2.04 meters per second squared. And the points that you get from this one is you have to use, oops, that's pink, hard to see, points on the line. Okay, that's 1 point. So if you use these points, they won't give it to you. And then finally, for an answer that is consistent with somewhere around 2 meters per second squared. And that is part 3. For the next part, this is where we get into the rotational part a little bit more. And this is part C. They want us to calculate the rotational inertia of the pulley, and they want us to do it in terms of MRA and fundamental constants. So if your answer doesn't show up like that, you will not get full points. I know that T times R, okay, so the tension times the radius, which is should equal I alpha. And so alpha here is equal to A over R. And for the block, for that block that is falling, we're going to say that we are positive is in the down direction. So here, let's go ahead and continue this. So this is TR is equal to I times A over R. So I here is equal to TR squared all over a, so our linear acceleration. At that point we can say the sum of the forces is equal to mass times acceleration since it is accelerating. mg minus t, since the block is moving down, we're going to call mg down positive, so that's why it's first, and then that's equal to ma. And now we can say t is equal to m times g minus a. So far, point-wise, we're looking at, for this first equation, 1 point there. We're looking at 1 point for recognizing we need to use the linear form. 1 point for this equation for just going through doing sum of the forces, making sure we have all this right, so that whole thing is really a point. And then our last point for just going ahead and finishing the problem here. So we've got I is equal to, now we need to put in t, and we said t is m times g minus a times r squared, and that's all over a, and that would be the last point. Now if you want to clean it up, you can. They won't give you any more points, but that'd be I is equal to mr squared, which is what we've kind of looked at before, times g over a minus 1. And whoops, that didn't look like a G. So that is part C. For the very last part, this is part D. It says the value of the acceleration can be found in B3 along with numerical values, and for given quantities in your answer to C can be used to total the inertia for the pulley. The pulley is removed from the support and its rotational inertia is found to be greater than this value. Okay, so they want us to give an explanation why. So you can either say that the mass or the radius is greater. So either the mass or the radius is greater, and that's because, so you get a point for that, and it probably comes from string wrapping. So you know when you wrap string around something, that radius will get bigger, and that would make r too big. You probably want to write out the word radius, or the mass is larger than it reads or measures on the scale. So those are some things you can think about, and you would get another point for doing the explanation. And that is the end of that problem.